this every time. You should learn to save the settings. Anyway, can I? Okay, I think everything is working now. So, any question from this time? This volume. Okay, so hopefully you are okay with homework. So if you have more homework questions, please consult TA. And anyway, we will teaching about quantum mechanics, and last time we go over this series formulation of quantum postulates, and let's go through them once again. So basically, every physical system we describe them as a unit vector in some vector space, and the vector space depends on your system. Basically, the more complicated your system is, the bigger the vector space should be. And so the state of your system, so all the information about your system is written in this cat file. And then you want to change your system, then you apply some unitary to this cat file, so that its length doesn't change. Then there's this weird quantum mechanics thing is being measurement. So the most general form of measurement are just state of operator mi with this completeness relationship. And basically, after you do the measurement, your state becomes this mi phi. And so there is some probability to become this state. That's the length of this square, length of this state square. And yeah, so if you measure this outcome, then you will know which I you get, and your state will become this state. And then you measure again, or you do unitary, you are starting from this state. Okay. So measurement also changes your state. That's something different from classical mechanics. And then we have this hidden postulate, which is saying that you have multiple systems and you want to consider them together, that the composite system, so when you consider everything, should be this H1 times H2 tensor to Hn. So as you might already know, there will be entanglement between the systems, and that will be kind of weird. Okay, and then we run through this example, okay, etc. Then we talk about, so the first thing about weirdness in quantum measurement is that there are indistinguishable states. Okay, so in classical state, so maybe, for example, this is 0, 1. So bit is in 0 or 1 is totally distinguishable. You can just look at the bit and classical bit, look at it, and you know it's 0 or 1. Okay. And but in quantum mechanics, some of the states are not perfectly distinguishable. Okay, so for example, we have this non-orthogonal states, so the 0 plus, and they are not perfectly distinguishable, so you cannot find the two outcome measurement, such that if you see the first outcome, you know it's 0, second outcome, then you know it's plus. And we have this very rigorous proof where we have generalized measurement M1 and M2, and we see that it's impossible to have them perfectly distinguish phi 1 and phi 2. Oh, sorry, psi 1 and psi 2. Okay, so we have a proof here. And so that's a quick review. If there is no question, then okay. So let's continue our teaching. And first, this is kind of a review again, so let's go really quickly. And once again, yeah, this is kind of a historical file. So it's we are repeating the 3 measurement thing. Okay. And anyway, so just as a review, once again, we have 3 kinds of measurements, so we just go to most general kind of measurement, and then we try to write the other 2 kinds of measurement as a general measurement. Okay, so first is we have projective measurement, and we see that if you have projective measurement, then those mi is just projector's pi, and where we assume the projectors are Hermitian, so pi dagger equal pi. Then we have a pi squared equal to pi as the definition of projector. And so completeness relationship, the sum mi dagger mi become identity, just become, so mi dagger is just pi. Then yeah, so the completeness relationship becomes sum pi equal to identity. And from here you can derive that with your Hermitian measure with your Hermitian projector, you can derive that means pi pj equals 0 for I not equal to j. Okay. Yeah. And okay, so you see that all the projectors basically project onto disjoint spaces because the product equals 0. And the probability of getting some measurement outcome is this phi pi phi. Okay. And then this is equal to, so yeah. Oh, remember. Wait. Oh, sorry, I'm confusing shortcut with PowerPoint. Yeah. Yeah. So phi pi phi, and so this is maybe change the color. Oh, it's okay. Yeah. So it's pi phi squared. Okay. And I guess here we are defining projective measurement a little different from the previous case we said. Here we are just saying the measurements are projectors, but from beginning, the thing we had before, we are saying the projective measurement you project into a basis. And I guess it's kind of ambiguous which people mean, and hopefully it's not too big a deal. So yeah, because the previous definition we have no degeneracy, but now we have. But I guess this one makes more sense because, yeah, because it's projectors. But anyway, we will not test you on the technical difference between degenerate projective measurement and non-degenerate projective measurement. And here we're just seeing how generalized measurement looks like, how projective measurement looks like in terms of generalized measurement. Okay. And yeah, then you see the outcome, then the state of the measurement is pi phi and renormalized. Okay. And a good thing about projective measurement is that the measurement result is fixed. So if you collapse into some state pi, some state I, so you got outcome I, then your state collapses into this pi phi, and then apply pi again, then you see that okay, so you should actually have some normalization here to make this more clear, although it doesn't matter. So square root of some normalization, square root of some normalization, square root of some normalization. Okay. So you collapse your state into this pi phi normalized, and then you apply pi again. Then you see that that's pi squared, and that's the same state. So so the probability of getting I again is 100% because you project onto pi again, then the length is 1. Okay. And that means that the measurement result is fixed. So if you do a projective measurement, and yeah, yeah. So if you do a projective measurement and you do the same projective measurement again, then you will just keep getting the same outcome. This is something we talk about. Yeah. So I guess this is weird in terms of quantum mechanics, but it is expected behavior you get from classical mechanics, right? Because you measure something and you expect it doesn't change if you don't change it. Okay. But as we have seen, this makes learning quantum states hard, because once you project into something, then some of its information is forever lost. So for example, then, so just like before, we have those A-B state. Maybe let's change the color. Okay. Yeah. So this is what you expect from classical mechanics, but it makes it hard to learn quantum information, because you have this A-B state, and then you know you will get A squared probability equal to 1, and B squared probability equal to 0. And then so you do this measurement, and so you get one chance to learn a little bit about A and B. You will draw with this probability. Oh, why am I? Sorry. So I'm reversing a 0 and a 1. Yeah. So you will get a sample from this a squared probability and sampling of a squared probability and the b squared probability once. Then, but you keep doing measurement and you just keep getting 0 or keep getting 1. And yeah. So once you've done the measurement, then basically the information about A and B is gone. You just get a 0 and a 1. Okay. So that's the weird part about quantum mechanics. Yeah, and more notation. So usually you call this projective measurement as measurement, and the one with MI as the generalized measurement. And then there's this physical measurement of you measure some some Hermitian matrix. So it's just you assign each projector to some number, and then you can write them together into a Hermitian matrix like this. So if you projector onto the first dimension with eigenvalue -1, and projector onto the second 2 dimension with eigenvalue 2, then you get this matrix. And then we can interpret this matrix as the physics observable of sometimes you measure it, you get -1 value on maybe your electrical charge or anything. And sometimes you measure it, you get 2, etc. So 2 electric charge, -1 electric charge, maybe. And yeah. And then you measure it and you collapse into the degenerate space. And as we said, you can think about the expectation value of your physics observable with respect to some state psi. And usually it's written as okay. So we have okay. So where we have this little band notation, we'll write this bracket A because it's band notation because we didn't say anything about psi, but people write this a lot. And yeah, you just need to read from context which side it actually corresponds to. But anyway, and the expected value will be this psi A psi. And here we'll show proof that you can check it yourself that is actually equal to summation of this different MI and the probability of actually getting into this MI. Okay, it's just by linearity very quickly. And yeah, so that's a quick review about the 2 other kind of measurement. Any question? If no question, then let's go to different topic. Okay, so first is this topic about phase. So we say a quantum state is some whatever complex vector psi, and we say any complex vector is some physical state. But is every complex vector a different vector corresponding to a different state? And the answer is actually not quite. So there is some global phase that doesn't matter on your complex vector. So you can think about, so if you have some complex vector psi here, and then you get another complex vector psi prime here, by multiplying this whole vector with a complex phase e to I phi. So basically you multiply every element of it by e to I phi. So if it's 2 by 2, then this will be e to I phi, sorry, e to I theta, not e to I phi. Okay? Anyway, assuming everyone knows scalar multiplication. So you multiply every coefficient of it by e to I phi. Okay? And we say it's really the same state because when you try to get the classic information out of this state, those 2 states, psi prime and psi, and you will get exactly the same outcome because when you do whatever measurement mi, and state of mi, and the probability of getting every measurement outcome will be same when you use phi prime or when you phi. So you can just do direct calculation. So the probability of you get outcome I when your input state is psi prime is psi prime mi dagger psi prime, and then you write this in terms of psi. Then you have psi prime becomes psi e to I theta, and say from bra become say bra and e to the minus I theta, because when you do a degree operation on this thing, you get a complex conjugate on your e to I theta, so you find e to the minus I theta. But this e to the minus I theta and e to I theta are scalars, so you can multiply anywhere, and in particular they can multiply each other, and you see that's 1. And so if you get rid of those two things, then you see that you just get the probability of getting I if your input state, getting outcome I if your input is xi. And here is a fully general argument. We didn't get any constraint on mi, so any measurement you will get any set of measurement you get a same outcome probability distribution. So we think those two states should be physically indistinguishable. They are just the same state physically. Okay. And so that's global phase. Global phase doesn't really matter because you cannot discriminate through measurement. But also there are something about relative phase. So relative phase doesn't matter. What we mean by relative phase is what about the phase vector in front of some coefficient. So for example, those two states you can kind of think of this as, so it's with 0 superposition of 1, right? And by you put a different phase, so you put e to I phi in front of this 1, but not from the 0, then it will become different states. So for example, you put a -1 phase here, then as we say, those two states are actually orthogonal and they are perfectly distinguishable. And so you can physically tell the phase difference between 0 and 1. Okay. So you cannot tell the difference when you put -1 on everything, but if you only put a -1 in front of 1 or -1 in front of 0, then you can tell the difference. So relative phase matters, and the global phase doesn't matter. And so that's the little weird thing about quantum mechanics. Okay? Okay. If everything is fine, then let's go to the interesting part of today's lecture. Okay, so let's talk a little bit about physics. And the physics example hopefully will give you more intuition about the quantum measurement, or make you think the quantum measurement is really weird. So it's this famous Stern-Gerlach thought experiment. I say thought quotation mark here, thought parentheses here, because part of it people actually done, part of it is just imagination. Okay, so let's talk about the actually done part. What does this measurement do? So the measurement is done like this, and so people will heat up. Excuse me. So there is a box here, and there is a whole bunch of silver atom here, and people heat them up, and they will shoot out this box, and hopefully kind of like a straight line. And there is a screen here, so so your silver atoms will get hit on the screen, and they will deposit on the screen, and you will get some kind of dot structure here. Okay, so there is a blob here, and ideally you want a dot, but there is always some error, so it's actually a blob here. Okay? And here we want to say a little bit about our coordinate system. So the drawing is a little weird because we draw our x-axis in different way, but anyway, so we assume I should probably use this direction is x, and the upper direction is z, and the direction the being is traveling is y. Okay. So when we look at it from the top of the screen, so it look at this x and the z. Okay. So this is just we are labeling our space. Okay, and okay, so you can shoot out silver atom, and it will look like this. And what does this experiment actually do? So this experiment want to test the spin of the want to test the spin number of the silver atom. So we think, so this is something about nuclear physics, but you probably heard that for a lot of atoms, we think they have some kind of spin. So it's like they are kind of like a small magnet. So there is a south pole direction and a north pole direction. So there is a spin of them. And so because they are kind of like magnet, so when you put them in a magnetic field, then you expect it to be affected by the magnetic field. So if the spin direction is pointing up, then it should be okay. Then I a little bit on physics, but anyway, it's one way or another. So your spin direction is like more up, then you will be pulled by the magnetic field to up. And if your spin direction is down, then it will be pulled by the magnetic field to down, etc. And you kind of expect if the spin direction is sideways, then it doesn't get pulled up or down. Okay. Okay. So people actually done an experiment and they shoot out the silver atom and through a magnetic field. And because it's totally random, so you kind of expect the spin on the atoms to be totally random direction. And you are pulling up and down, so you kind of expect this kind of blob. So this blob getting pulled, some of them getting pulled up, some of them getting pulled down, and maybe you have a Gaussian distribution or something. Not Gaussian, but you have some spherical distribution because the spin direction is totally random. But this is not what people actually get. People find out that the spin of the silver atom is actually quantized. So when they do this experiment, they see two distinguished blobs. Okay, so yeah. So once again, the magnetic field in z direction, and they see on the z direction, then whole blob of spin is getting pulled up, and another blob of spin is getting pulled down. So it's like the spin of the silver atom only have two values, either pointing up or pointing down. And there's no this three-dimensional geometry, three-dimensional continuous distribution of spins. And that's what you expect. If you have that, then you expect you get this thing. But they have these two discrete blobs here, and they see the result is being quantized. Okay. And yeah, so this is, I believe, I guess one of the first experimental evidence that there is quantum mechanics in this world. Obviously, there are other things. But yeah, so this is a very straightforward experimental conference where you see that the spin value is not continuously distributed, it's just these two possible values up and down. And now in our language, we think about, we can say that then this means that the spin is described by a two-dimensional space. Okay? So the spin, although it's a three-dimensional vector, you think it should be a three-dimensional vector, but actually just described by one qubit. So it's like when you go through the magnetic field, you are doing a z direction measurement, and so post measurement outcome, you have a measurement outcome 0, then it's upper blob, and the measurement outcome 1, and you get a lower blob. Okay. So yeah. There are only two dots, so we think it's a two-dimensional space. And we actually have a theory to make this all making sense. Okay. But for now, so yeah, so what happened? So we will have some kind of distribution. So we say it's a qubit state, and we know a qubit state is described by this vector a and b, with a squared plus b squared equal to 0. And so the atoms shooting out actually have some kind of distribution on this AP, and but whatever the AP is, will get measured in the z direction, and they get a squared probability going to up and a b squared probability going down. Okay. So it's kind of like yeah. So one of the way I like to think about this case is the spin here being a two-dimensional system is really dumb. So when you ask the question, you only answer you yes or no. So there is only, yeah, because it's only two-dimensional, so you can only answer 0, 1, or yes and no. So you only answer up or down. Okay. Okay, so this is part people actually do experiment. Now we are going to solve the experiment part. So now it's a little bit theoretical, but we believe that these are all true. Although actually doing experiment is very hard, so I believe people haven't done this in this kind of setup. Okay, so what is the sorted experiment? So the sorted experiment is what if we do this measurement multiple times. Okay, so we shoot out we shoot out a spin, and then we do z direction magnetic field, which corresponds to z direction measurement. And as we say, we'll split into two dots, and so you should probably split into two strings. So there is a 0 string and there is a 1 state string. Okay. And what happens if we take this string? Okay. So those string, everything here is a 0 state, and then we measure in x direction. Okay. And well, we expected it to also split into two dots. There are only two possible two dots because it's dumb. It only answer yes or no. Okay, and anyway, we think it will be this two dots in x direction. And so here is something I claim, but anyway, there are physical ways to justify why this is true, but the x direction measurement is actually measuring this sigma x Pauli operator that I say is very important. Okay. And yeah. Okay, and we also make this because yeah, and also I can say the z direction measurement more formal here. Okay, so z direction measurement we say is a computational basis measurement, but you can also view it as measuring the sigma z, because measuring sigma z, as we probably seen before, so sigma z, there are two eigenvectors, are those two computational basis vectors, so 0 and 1. And so instead of seeing it as computational basis measurement getting 0, 1 outcome, you can see it as doing sigma z measurement and getting the outcome being the eigenvalues 1 and minus 1. Okay, so you see this makes more sense. So it's like pointing up, then is your vector is this 1 up, and the point down then is minus 1 up, so it's pointing down. Okay, but anyway, so the sigma z is doing z basis measurement, and the sigma x is doing x basis measurement. Although we didn't give proof here, but you can see the naming here makes some sense, because they correspond to x basis measurement and z basis measurement. Sorry, I should say x-axis measurement and the z-axis measurement. But anyway, so assuming this is true, measuring x direction is a sigma x, then when your input is 0, and then we decompose it into the eigenvectors, and as we say, the eigenvector is a plus state and a minus state. And then we have seen this calculation before. So the probability you're getting outcome plus is so you can calculate this projector of 0 on this plus outcome, then it's 1 over square root of plus. We have the subnormalized state, and from here you can calculate that the probability of getting this is 1 over root 2 square, so it's 50%. Okay. And on the minus is saying it's 50%, and when you so you get measurement outcome plus, then your state become plus, and you got plus direction of x, so you got this one, so this is plus, and so this is plus, and this is minus. Okay. So you get plus 1 outcome and minus 1 outcome. Okay. And and we can think about, okay, so now we think about different kind of way to cascade the spins through those measurements. Okay. And so we say we can do z measurement and x measurement. Z measurement and take the 0 state to do x measurement. And what about you do z measurement and taking the upper state and do through z measurement again? And I guess this is where we can ask you a question, but I already have answer here. Okay. And if we do this, and then this is something we keep saying. You are doing repeated measurement. So here you are doing the result expected by the classical thing, right? So you see your state is already pointing up, and then you measure it again, you think it's still in this 0 ket. So your spin is still pointing up, so you should only get one blob up here. One blob up here, because yeah, you are measuring 0 with, okay. So once again, we can do the calculation. So we are measuring this 0 ket with this sigma z measurement. Then the probability getting 0 is 100%, the probability getting 1 is 0%. Okay. And yeah, that's how we say. Successive projective measurement gives the same outcome. Okay, now get things really weird. What if we do things like this? Okay. Oh, here we have a question mark, so I can ask you a question. Okay, but let me describe this. So we shoot all the beams, and then we do z measurement, separate them into 0 and 1. Then we take a 0 string and do x basis measurement, and separate into plus and minus. Then what happens if we take the plus string again and do z basis measurement again? Then what should be the outcome do? So anyone want to answer? How many dots should be there? Anyone? Okay, so it should be plus state. What happens when you measure plus state with the z basis? Okay. And yeah. Anyway, you measure plus state with z basis, and you know the z basis measurement outcome should be. So there should be two possibilities, right? So the z basis measurement, so once again, is x to z. So you do z basis measurement, then there should be one location corresponding to 0, one location corresponding to 1. And the question is, what's the weight between them? Should it be 50-50 or should be only one of them? Okay. And so if you go through the math, then you see that this is the thing we have done. So you measure this plus day in 0-1 basis, then it should be 50%, 50% again. Okay. Okay. So it should be 50-50 again. And okay, so it's split again. And okay, so this is totally legit according to rule of quantum mechanics. But then you think about this in kind of classical interpretation, and you think it's really weird. Because you think you are already picking up a 0 state here, right? You are already choosing a 0 state here when you do a first Z measurement. But why do you get one state? Okay, yeah. So you are starting with a 0 state, then, yeah. You are starting with a 0 state here. But when do you get a one state outcome here? Okay. Your state should be 0. Okay. And yeah, so this is the weird thing about quantum mechanics, and something I was saying is that the measurement will totally change your state. So when you do the x measurement here, then your state will turn to plus, and it totally forgot it come from 0. Okay. And that's the weird thing about this quantum mechanics. So in this two-dimensional system, I like to think the particle is kind of dumb. You only remember yes/no answer, and yeah. So when you answer yes/no in x direction, then you forgot. You only remember one yes/no answer, and you answer that is yes in x direction, then you totally forgot whether it's yes or no in z direction. Okay. So when you ask it again, are you so answer that in the yes of x direction. Then when you ask it z direction again, then you forgot you was answering 0. You just answer with 50-50 probability again. Okay. And you can also view this as the measurement will collapse the quantum state. So this measurement x collapses the quantum state from 0 to plus, and it just change from 0 to plus forever. Then the following measurement you do on this plus state has no relation to whether it comes from 0 or 1 or whatever. It's just a measurement on plus state. Okay. So that's Sternberg experiment, and so it's a way to show you how collapsing a state will actually change the state. Okay. And here, then here we change the organization of my node a little bit, and now is a good time to talk about the block sphere and the polys. Okay. So I say I won't prove that the x direction measurement is only actually poly x, but I can kind of justify a little bit by showing you this block sphere, which has a really close relationship to all the poly operators. Okay, and it's also a good way to visualize one qubit. Okay, basically a way to visualize the spin operator here. Okay, and so we start with okay, so this is a book derivation, so it's triple one, but it's a little weird derivation. But anyway, we started with saying that any state psi is, well, obviously it's a0 plus b1 with a squared plus b squared equal to 1. Okay, and then we can parameterize this in different way. Okay, so we want to, okay, so a squared plus b squared equal to 1. We have two complex number, and two complex variable means 4 real variables. Okay, and we can change to different 4 variables, and actually we only have 3 variables. Okay, so we have 4 variables, but we have this constraint, so we only have 3 variables. Okay, and so from this constraint, we can say the norm of A is some cosine theta over 2. Okay, so this one is norm of A, and there is over 2 because the reasons that we will not say. Okay, because it's convenient. And so norm square of A is some cosine theta over 2, and norm square of B is some theta over 2, sin theta over 2. And there is some phase on A and some phase on B. So we say the phase of A is this e to the I gamma, and the phase of B is e to the I gamma plus phi. And then we say the global phase doesn't matter, so our state is just this cosine theta over 2 0 plus e to the I phi sin theta over 2 1. Okay, so why do we want to do this? Because want to do this, then we can plot this phi in as a point on a sphere. Okay, so we think about this x, y, z direction, then then we can draw any point on a sphere with this spherical coordinate, and so spherical coordinate is I guess, yeah. So you rotate it from z down with some angle theta. So I just kind of want with theta to be over 2. So want a theta between 0 and pi, and phi between 0 and 2 pi. Okay. Okay. And we can write this point with this theta and phi. So we go down from z with theta, then we rotate the z-axis rotate the ball the z-axis by phi, and we'll get this point. So every point can be described by this theta phi pair, and that corresponds to the theta phi here. Okay. Yeah. So every point on this surface corresponds to this a0 plus b1 with this theta phi convergence. Okay. Okay, but so now it's just an arbitrary way to write your arbitrary state, to map your state onto the surface. But this surface has more structure. So actually, every axis corresponds to poly matrices sigma x, sigma y, sigma z, and as we say, every point on the sphere so there is a one-to-one mapping between the point on the sphere and the 1 qubit state, meeting the global phase. Okay. And actually, you do unitary operation on your qubit, then it will just be a rotation on the sphere. Obviously, it's a bit of phase, and this is a little hard to prove, so we won't do proof here. But this is true. So that means the mapping is not arbitrary. So actually preserve structure, and So you do unitary operation on this phi is actually a rotation about some axis on this sphere. Okay. And for example, I should give more example here. Sorry. And anyway, yeah. For example, sigma x. So sigma x operator, the sigma x is 0, 1, 1, 0 once again. It will be a 180-degree rotation on the x-axis. And I guess we should give some example here. Okay. Oh, so example here. Okay. So you plug in this formula, you will see that this x, y, z axis actually correspond to the eigenstate of x and y and z. Okay. So so you see the 0 and the 1 vector is on the z-axis. So the z vector is, yeah. So you map the a equal to 0, a equal to 1, b equal to 0 through everything here. Then you see that you are on here because the theta equal to 0 and the phi doesn't matter. And a equal to 0, b equal to 1 is this, I guess, theta equal to pi. Theta equal to pi, then sine theta over 2 equal to 1. So that's here. And then you have plus state, so square root 2, square root 2. Then that's theta equal to pi over 2. Then theta equal to pi over 2. Then you have cosine pi over 4. And cosine equal to pi over 4 equals sine pi over 4 equals square root 2 here. And that's phi equal to 0. Right? Phi equals 0, so you have a plus between that. Then the minus state here should have the sin theta. And the phi being equal to pi, so e to the I phi is minus 1. Okay? And so you see that this this mapping from your quantum state to black sphere actually has this very strong geometric structure, and they actually correspond to the spin we're talking about, right? So it's like your spin is pointing in z direction, and then it corresponds to this, yeah, how should I say? So you can think about this is how the spins are getting mapped into A0 and B1. So if your spin is pointing in x direction plus x direction, then it's actually mapped from this correspondence, you map to the plus state. And your spin is pointing in the minus x direction, you map to the minus state. And you will maybe say it here more, right? So your plus direction, then your spin in plus direction, then you map to the plus state. And in the minus direction, you map to the minus state. And in the plus z direction, then map to the 0 state. And in the minus z direction, map to the 1 state. Okay. So, so before we only told you 4 possibility, but here you see that if you do any direction measurement and get any eigenstate, then then you see what the corresponding A0 plus A and B on A0 plus B1 is, just from this correspondence. Okay. Yeah. Yeah. So the box sphere, you can see this as how a two-dimensional system represent a spin. Yeah. And okay, so we told you how the state map on how the state correspond to this sphere, and actually the measurement also. Okay. Okay, let's talk about this first. So the measurement also correspond to some direction on the sphere because you are measuring to some direction, right? So you can, okay, but here we are using different coordinate systems, so it's a little confusing. So yeah, so before when we talk about spin, we were talking about we map on the sphere with this theta phi notation. And but when we talk about measurement, we actually want to do the Cartesian coordinate. So we are thinking we are measuring in some n-hat direction. So this n-hat is three-dimensional vector. So this is on n, x, and y, and z. Okay. And yeah. And so the corresponding measurement operator is actually this inner product between n hat and the sigma vector. Okay. And okay. So what the sigma vector is, so this is a little confusing notation. So sigma vector is a vector where the elements are poly matrices. Okay. So it's sigma x, sigma y, sigma z. Okay. And so what do we mean by the inner product between n hat and the sigma vector? Is this inner product between three-dimensional vectors. So it's nx sigma x plus ny sigma y plus nz sigma z. Okay. So it's just a 2x2 matrix. So it's a linear combination between poly matrices. Why is it so slow? Okay. Too many erasure. And anyway, nx sigma x plus ny sigma y plus nz sigma z. Okay, so it's a 2x2 matrix. Something 2x2. Okay. Maybe drawing other way. Maybe I just say 2x2 matrix. 2x2 matrix. Okay, it's a linear combination between sigma x, sigma y, and sigma z. Okay, and yeah, and this matrix is a 2x2 matrix, and it's easy to see its Hermitian. And so it's a Hermitian matrix, and then you can think about measurement against this matrix. Okay. And actually, this matrix is a lot like a poly matrix. Okay. So poly matrix sigma y, sigma z, sigma x, sigma y, sigma z. And yeah, because there's symmetry beyond this whole sphere, so really measurement in some direction, measurement in any direction should be kind of similar. And in particular, so whatever n hat you choose here, the eigenvalue should be +1 and -1. So yeah, in this way, in this point sense, they are all like a poly matrix. It's just like poly matrix in different direction because they are eigenvalue +1 and -1 just rotated to different direction. Okay, and a good example is our friend Han-Hsuan matrix. So Han-Hsuan matrix is actually a linear combination between X matrix and Z matrix. And yeah, you just do addition and you see that it's a 1 square root to 1, 1, 1 minus 1. So Han-Hsuan matrix is like a poly matrix in the middle of X and Z. That's why when you do rotation about this Hedema direction, then you actually swap between the x-axis and the z-axis. Okay, so you probably see, so applying sigma x is 180-degree rotation on x-axis, and so applying Hedema is actually a 180-degree rotation about this Hedema axis. So Hedema axis, and this is about 1 square root to 0, 1 square root 2. They correspond to 1 n hat. Okay, so here. And yeah, so you can think about you rotate around this axis, then x goes into z and z goes into x. Okay. So that's why you have symmetry here. And okay, so you have measurement and you have state, and they actually match up. So I guess this is something I can get you do as an extra homework. Okay, but it's just brute force calculation. Okay, it can be checked in homework. Sorry. Oh, yeah, and so from here, okay, sorry, the organization here is a little weird, and we are over time. But anyway, Those two things are actually related. So the state in the NK direction, but actually okay. So it's really confusing. So you think about a point on the sphere. Okay. So any point on the sphere and there is a state that we return in polar coordinates is theta and phi, and there is a Pauli matrix that you return in terms of nx and y and z. But anyway, they are related to each other because if you are on the same point here, although we are writing different coordinate system, so this state is the plus one eigenstate of this matrix. Okay, and the other direction is the minus one eigenstate of this matrix, and you can check in homework. Maybe, yeah. And so if you plug in this formula, then you see the eigenstate of Hedman is those two vectors. Okay, let's sorry for overtime. Let's take a break for now, and let's continue more about path sphere next class. Okay.怎么了？
你现在讲的这个 slide 在议论上面是没有的。
它在那个 density matrix 那里，我会上传，抱歉，不要忘记了，我现在上传好了。这样子你们可能比较简单，因为你们是直接连网络吧？那我直接，可不可以？应该可以吧？我试试看哦，我直接去议论。
去年的。
对，议论其实今年有改，但是我今天有改，所以对，你要议论的要找类似的话，你要去找 density matrix 那个 density matrix 的最后面。
哦。
对。
OK。
对。但是对。
刚讲那个确定 homework 是什么？就是你刚说那个 homework 是。
就是我可能会加一题让你们写的，就是你去证明说这个东西真的是这个东西的 plus one 跟 state， 对啊，你应该是算一下就可以了，对啊。
老师还用到这个，就是第一个是说那个一个框架会有它的系数可以是 complex number， 还是
对的，都是 complex number。
那我想问说，这个作用它是怎么作用？就这个 EIC 的那个和 side 的相乘。
就是你把所有 coefficient 都乘 EIC 它是一堆 complex number 嘛，那每个 complex number 都可以乘 EIC 它。
那所以如果今天如果我的 theta 是90度的话
，theta 9度不知道什么，好像是 I 吧。
所以如果我这个原本是0，那我这个就会是1吗？
不会，它会是 I 乘以0。
它是作用在系哦。
不是作用在 basis 上面的是那个。
我知道。我觉得就有点奇怪，作用在系数。
对。还有 A 跟 B 嘛，就会变成 EIC 它的 A 跟 EIC 它的 B 这样子。
哦。
对。上传一下好了。资讯，不是小五资讯，把这个关掉。云翠，我跟你讲一下，那个就是作业1， 你开了，就是我修改一下，就是你有什么通知评分者的，然后他们就一直送 email 到我的信箱，所以我把它关掉。
哦，OK OK，好，
不知道你有没有
所以
需要？
你说
好吧，我不
批改者，我再把那个
就是好像
下次打分
下次就是我不知道，不知道能不能设定对他通知这个被我关掉。
哦，OK OK OK
对，因为会一直寄到我的信箱。
OK OK，
就你有很需要它吗？还是
没关系
OK？那就先这样。嗯。我是才给一个02的。OK。 Hello. Okay, let's get back. And so as we said, black sphere is a good way to think about spin direction of a particle in a real world. So those actually we call like, well, in physics we will say spin heavy particle. But anyway, so it's a particle whose spin is described by two-dimensional space. Then we can visualize it as a black sphere. So if you think a particle is spinning in some direction, then its state corresponds to the it has a quantum state correspond to that point on the black sphere. And so there is a theta and a phi, and you can calculate A and B from this equation here. And yeah, so there is some caveats here, but although there is a very strong geometry, so there is this XYZ in real world geometry on this black sphere, but and we say respect a lot with this geometry on the quantum state, but this XYZ geometry and the two-dimensional geometry are actually different. I mean, different means that, for example, the inner product on the black sphere doesn't equal to the inner product on the quantum state. Okay, so I should say the quantum state here. Okay. And so that means if the quantum to quantum state are orthogonal, doesn't mean the vector on quantum state is orthogonal in particular. Okay, so for example, you think about 001 and 00 minus 1. So this state and this state. So on black sphere, those two things are not orthogonal. They are on the same line. Okay, but as a quantum state, the 0 state and the 01 state are orthogonal. And also, for example, is 0 state and the plus state. Okay, so one of them is on z axis, one of them is on x axis, and yeah, one of them on z axis and one of them on x axis. So it looks like those two states are orthogonal on the black sphere, but we know that plus state and so plus state and 0 state are not external to each other. They are not orthogonal. So yeah, so the geometry and so the geometry of black sphere and the geometry on quantum state is still a little different. So also this 0, 0, 1, 2, 0, and 1. This is a better example. 1, 0, 1, 1, 0, 0, 2 plus. Okay. So it's orthogonal here, but it's not orthogonal here. Okay, so that's black sphere, and okay, and there's something extra here. So a little extra thing. So you have a really nice description of two-dimensional space here, but you might think yourself, what about higher dimension? Higher dimension, you also have a higher dimension, but actually, so we will try to do it, generalize the black sphere to higher dimension, then it's very hard. So people have tried, but they don't find things as nice as this. Okay. How to generalize. So that's just something extra. Black sphere. I guess this good property. Let's just say, yeah, whatever. How to generalize black sphere to more dimensional space. Okay. And okay. So that's the most technical part of black sphere. Any question? No. And yeah. And then we can go to a bit of theoretical thinking here. So we talk a lot about this two-dimensional space, this A and B space, and yeah, through this Stern-Gerlach experiment. And so we see that it's kind of stupid because whenever you do a measurement or a projective measurement, you ask a question. Yeah, so when you do a projective measurement, you only have two answers, and then you only give you one bit answer, and it tells you this one bit answer, and then you forgot everything else. So you kind of only have one bit of information here. But also you see that it can kind of represent everything on the sphere. So it's kind of like a three-dimensional vector. Well, more like a two-dimensional because it's on sphere, so only theta and phi. So it is 3, but kind of like 2. But you see, and that's from this A and B coefficient. Yeah. But yeah, so this seems like a lot less information than this, and that's interesting about quantum state. But it's how much information does it actually hold? When you do a measurement, then sometimes it seems like it's holding very small amount of information, just kind of one bit with some probability. But if you think about how to actually describe this thing, then you see you need to describe it with two independent random variables. Okay, and yeah, and that's like one of the central questions in quantum information. That's how much information does your quantum state actually hold? Okay, and really depends on how you assess it, how you do the measurement, etc. Okay. So here I should, yeah, is a vector in three-dimensional space, but kind of like two-dimensional vector. Okay, so that's a lot of analysis on one qubit system. Any more questions? And I think I will have you prove some of the fundamental things about all this, the Bloch sphere property I can. So maybe you will prove this and this. Okay. And okay, so that's two-dimensional system. Okay, and let's go back to talk something more general. Okay. So different concept, POVN. POVN stands for positive operator value measure, and is a lot of historical reason to why it's called this. Historical and mathematical reason. But that's not important for us, so just remember that called POVN. And so what's the POVN? And there's something you can get from any measurement. It's like a measurement, but you are losing some information. So remember, a generalized measurement is described by a set of those measurement operator Mi. And from then you can write POVN just also a set of matrices EI, and those EI are just this Mi dagger Mi. Okay. So from obviously you can calculate this thing. So you have a set of matrix, then you can calculate another set of matrix, those EI. And so this whole set is called POVN, and this EI, we call it a POVN element. Okay. So I want to do this. First we prove that this EI are still pretty useful. So in particular, you can using those EI, you can calculate the probability of getting some measurement outcome PI. Because those PI is phi Mi dagger Mi, and you see that they only depend on Mi dagger Mi, doesn't depend on the individual Mi. So in particular, so that's there's psi EI psi. Okay. So you can calculate this probability by just knowing EI, and and the completeness relationship can also return in EI because we had some Mi dagger Mi equal to identity, and that just translates into some EI equal to identity. Okay. And okay, so we can calculate the measurement outcome probability, but we say we are losing some information because we are doing this kind of squaring thing. And the thing is, we don't know the post measurement state anymore, so we don't know MI psi anymore. Okay. And yeah. Okay, so but sometimes you don't want to specify your measurement so much, so then you just so sometimes you don't need to know the post measurement state, you just want to calculate probability. Then describe the measurement in terms of EI, then MI is nice because I guess for one thing, then when you write the measurement probability, you just need to write MI instead of MI. You just need to write EI instead of MI dagger MI. So that makes the notation much easier. You are writing a lot less things. Okay. So that's POVN, and usually it's used in describe non-projective measurement because, well, in projective measurement you don't really need to do this simplification because if MI is projector, then MI dagger MI is just so if MI is on projector PI, then as we say, the PI dagger PI is just PI. So if projective measurement and the POV element just send as your measurement operator element, and you are just writing the same thing. Okay. So usually use this to describe some weird non-projective measurement that you don't really care about the measurement outcome, you just want to calculate probability. Okay. And okay, so we say every measurement can be written as a POVN in this way, but actually there is kind of converse. So you have a set of element, POV element like this. So you have a whole bunch of EI such that first every EI need to be positive, semi-definite, because they come from these things, so come from this M dagger M structure, so they must be positive. So you have a set of EI, they are all positive, and like satisfy completeness. Then it's a POV, meaning there is a measurement that will give this kind of POV elements. Okay. And here we just have a constructive example, so you can take MI as the square root of EI. Because you are positive semi-definite, so you can take a square root by basically taking a square root of all the eigenvectors. Okay. And once again, here is a reminder of positive semi-definite, and it's just that is the inner product to all the state size is greater or equal to 0, or all the eigenvalues are greater or equal to 0. Okay. And yeah, so whenever you have set of matrices satisfy that they are OPSD and they sum to identity, then you can think of it as some kind of measurement. Okay, so it's a POV. So that's a theorem, and we do a really quick proof by just saying there is a corresponding MI just square root of EI. Okay. So that's really nice. And so let's show how we use this to prove something with much less notation. Okay. So we have this generalized measurement to distinguishing non-orthogonal states. So here we have quotation mark on this distinguishing. And because we already told you that a non-orthogonal state cannot be perfectly distinguished, so now we have this quotation mark distinguishing, and what do we mean here? It's not perfect distinguish. Perfect distinguish is you have two states and you want, so maybe I draw a little here. So perfect distinguish means that you have two states and you have two outcomes, and one this state go to this outcome and this state go to this outcome. Okay, and what is our perfect this quotation mark distinguish? So quotation mark distinguish is that we are actually using three measurement outcomes. Okay, so we have E1, E2, E3 here, and those are POV elements. Okay, and okay, so let's just have a spoiler here. So what happens is zero will. So when we input state 0, then you only go to E2 and E3. When your state is plus, then you only go to E1 and E3. And how does this distinguishing? Then this distinguishing because is distinguishing sometimes because when you see E1, then so what do you actually see? So you don't know. Maybe let's draw a line, right? So let's draw a cut here. Okay. So you don't know the input state. This is what you see, right? So you see that whether you get E1, E2, or E3. Okay. And so this is what our server see. Our server see. And our server see you get E1, E2, or E3. And so if you got E3, you don't really know what happened because it can come from 0 or plus. But you see E1, then you know that it must come from plus, and you see E2, then it must come from 0. And that's what we mean by distinguishing. Okay? So sometimes you can perfectly know where it comes from, but it's not that one-to-one to outcome we have. We have this we're undecided E3 here. Okay? And so this is what we are trying to prove. We got, and let's see that we actually get this. And what are E1, E2, E3? E1 is a projector onto the one state with some normalization, and E2 is a projector onto minus state with some normalization, and E3 is identity minus those two. Okay, and then can talk a little bit about this construction. So why do we have this weird construction? It's because let me use red here. Yeah, it's because we want 0 to never go to E1, right? And so what happened importantly is 0 never go to E1 and the plus never go to E2. So that's why we have this projector onto a orthogonal space of 0 and a projector onto a orthogonal space of plus. Okay. So 0 will never go to E1 and the plus will never go to E2. And now another question is why do we need this weird normalization here? Why would we only just have 1 and 1 here? And anyone want to answer? It's somewhere. Okay. So remember our POV need to satisfy this property. So we and we have E3 here, and so which one will property force that we need to choose the some coefficient here that's less than 1. It's either 1 or 2. Anyone want to try to answer? Okay, and I guess it's a bit both, but I'm thinking it's this 1 here. Okay, so we can always define E3 like this, then E1 plus E2 E3 plus E3 will equal to identity, right? Because well, by definition, like adding together it become identity. And yeah, and but we want all 3 of them to be positive semi-definite. So those 2 will always be positive semi-definite because they are proportional to a projector. There are some positive number times the projector. But if you have coefficient too big here, then you are subtracting too many things here, then E3 might have negative eigenvalue. Okay. So that's why we choose the perfect value here such that the E3 is still PSD. Okay. And yeah, so that's our construction, and I believe we probably don't have this homework, but you can check. It's still positive PSD. And anyway, then when this is actually measurement, then it will behave as we said. So because E1 is orthogonal to 0, so 0 never goes to E1, and E2 is orthogonal to plus, so plus never goes to E2. And so when you see E1 outcome, then you know the starting state is plus. You see this 2 outcome, then you know the starting state is 0. And you see this 3 outcome, then it's really undecided. Yeah. And so here we can say something a little more general. So this is so this distinguishing versus perfectly distinguishing is something funny. So you just change change the definition of what you change your definition of what you do a little bit, then it becomes so something not possible becomes something possible. Okay, and yeah, so that's why those learning quantum state thing is really tricky, because you need to specify what you want to learn very carefully, and so different setting will give you very different answer. And it's an interesting active area to see about, and to see about what you can learn on the quantum state. So for example, there is quantum state tomography and the quantum state discrimination. And I guess another thing is this example of this thing here, right? So you have this AB state, then you can either think about doing a measurement and only give you one bit answer, and maybe you do something else, then you see it's a three-dimensional vector. And I guess something interesting about the learning quantum state is a lot of time, so this is really information theory, and a lot of time when you deal with them, you care about is sample complexity. Okay, so what sample complexity is that, so with one bit, so if you only get one copy of state, it's really hard to learn it. So basically, we get is 0 and a plus. As we say, you cannot perfectly distinguish that. But if you get many copy of 0 or many copy of plus, then you actually can distinguish that, right? So maybe write the example here. So if you are either given 0, 0, 0, da da da, either or plus, 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 right? Then this is kind of distinguishable with pretty good probability, because then you just do computational basis measurement, right? Although this is not the base one you can do. You just do computational basis measurement, and this 0, 0, 0, 0 will always give you 0 outcome, and the plus will give you 0, 1, 0, 1, 0, 1, 0, 1. So whenever, so you get some bit string out, so it's 0, 0, 0, 0. Then this one give you uniform random, right? So you just need to do constant number of them, and you can kind of distinguish them, because uniform random string, you have very high probability, you have like exponential probability to get, okay, so 1 minus exponential probability to, sorry. So you only have an exponential small probability to see all 0 here, okay? And yeah, so doing only constant number of them, you have very high probability to separate this case or this case, okay? And so when you do the learning quantum state, usually you are in those kind of cases. So we are assuming you are in either one of the state, or either one of the state of the state, etc. Or usually it's one fixed state, yeah. So you are in either one of the state, and then you are given multiple identical copy, then you are trying to learn it. Okay. And so that's the idea of sample complexity. So you are given some state with many copies is n, and you are asking how many n do you need to learn phi. And here then we didn't write the tricky part with respect to some text. Okay. And so this learn is the tricky part. So what do you mean by learn is you want a different kind of learn, then you have different kind of complexity. Okay. And yeah, so here we see that the thing you want to learn is either 0 or plus. And you see you use constant copy, then you have pretty good probability to distinguish that. Okay. Yeah. And so that's a small digression into learning quantum state. Any question? Yeah. And let's talk more about quantum information. Okay. So we have this important theorem, or famous theorem, saying no cause theorem. Yeah. And it kind of, I guess it's a very good structure here. It kind of justify why we need many copies. Okay? Because in classically, you kind of think that you can just, if you can copy paste your state, then you can just take one copy and create many copies and do measurement on each copy independently. Then you can always learn everything with one copy. But that's not possible because there is this no cloning theorem. That's kind of the basis of quantum information theory. And it says that, well, the high-level idea is you cannot just get a quantum state and get many copies of the quantum state. And in more mathematical form, it's written like this. Okay, so we say every quantum operation should be unitary. So if you want to clone the quantum state, then you should also have a unitary. And you think the unitary should do this. And although we say n copy, then we should always start small. So let's say we want to copy from so we want to copy from one state to one copy to two copy. Okay. And yeah, so so copying unitary should do this. So you start with from some whatever state, and then there is another clear register, and it should be whatever standard basis. So that's within 0. Okay, and so this should be some like a blank paper you want to write your state in, and so your copying unitary should read this state and then write it into the blank space. So you should get a 2 copy out. Okay. So you should have a copy. A copying unitary should do this, and you should copy any state. Okay. And we say that. So we have a non-cloning theorem, and we say this kind of unitary cannot exist. Okay. And one important thing here is, okay, so okay, let's just use black. Okay. And for this theorem to work, it's actually important to say for quantum state, although you don't really need all of them. Okay, so let's just see the proof. Okay, and so proof. Assume we have two different quantum states that we both want to copy with this U. Okay, and so we just write down the equation. So this should happen. So U phi 0, so U psi 0 should be psi psi, and U phi 0 should be phi phi. Okay, so and yeah, I guess we didn't write the notation very carefully, but this U here. Okay, so this is a little ambiguous, but there's really no way. So this U, so we have two registers here, so we are thinking these two are tensor in each together. And the U is a huge unitary, as you see, probably guess from here. U acts on both of them. Okay, so it's not U tensor identity or something. So U acts on both of those registers. Okay, that's why you can copy. And anyway, so we have those two equations. And then we can just take an inner product of both sides. So on the left hand side, the inner product, so you basically flip everything. So you flip this, and this become psi bra 0 bra, and okay, so those two things. And so remember, when the tensor product ordering doesn't get flipped when you do the dagger, so this is psi 0, it becomes psi 0. But the U is doing matrix multiplication on those two things. So U should come after them, and then become U dagger. And then you times your U phi 0. Okay. And on the other side, you just have this psi psi multiplying phi phi. Okay. And here we use that U is unitary. So in the middle, we have U dagger U. And that should just be identity matrix. So you get rid of it. And then you do the inner product on tensor space, then we say just a slot matching slot. So you have psi inner product phi here and 0 inner product 0 here. Then you have psi inner product phi times psi inner product phi. And so now both of the sides are scalar. So scalar times scalar, scalar times scalar. So it's good. And also we have a 0 inner product 0 here, so it's just identity. Okay. And okay, so you want this equation to hold true, but you see that every term is the same. So if you call this x, then you just have the x squared, x equal to a squared. And this thing actually have a solution. So if a solution where the inner product is 0 to 1. Okay. And so what happened? So we prove something actually a little more than this. So we say that if you want you to have a cloning unitary, then sometimes it works, but they only work on very small set of state. So it actually can only act on the set of states that are all orthogonal to each other. Okay. Yeah. So because this condition only satisfy in, so there is a 0 and 1. So when it's 1, then that just means your side equal to 5. Okay. And if it's 0, then it means orthogonal. So it's perfectly distinguishable, right? So we already proved that if two states are orthogonal, they are perfectly distinguishable. And then you can, okay, yeah. Yeah, so this cloning thing can only work on perfectly distinguishable state. So basically like a classical state, because yeah, can kind of think a perfectly distinguishable state are kind of set of perfectly distinguishable state are kind of classical, although this interpretation is also weird, a little weird. But yeah, so if you consider two states, then there need to be orthogonal for them to be both clonable at the same time. And I think you can extend this to if you want to clone a lot of states at the same time, they need to be all orthogonal to each other. Okay, so they kind of form an orthogonal basis. Yeah. I guess every pair is orthogonal, so of course they are all orthogonal to each other. Yeah. Yeah. So that's no cloning theorem. But if you so if you're two state orthogonal, then you can it's possible to clone them. I guess we didn't prove that it's possible, but it's pretty easy. But the actual thing you want to say is if the relationship between those two states are kind of quantum, so they are not totally orthogonal to each other, then it's impossible to do this cloning here. Okay. Okay. And I guess a little digression is that so if you don't want perfect cloning here, so if you allow yourself to be a state that's kind of close to this thing but not quite, then it's possible to do this on orthogonal state. And obviously the more close of those two be into orthogonal, then the less error you get. Okay. Yeah, the less cloning error you get. And that can be formalized mathematically, but it's kind of out of scope. It is not for now. Okay. So that should finish our quantum information theory part. So yeah, so you see those non-orthogonal states are really weird. They are not distinguishable, they are not clonable. And when you measure them, you kind of lose the information on it. Okay? And learning those non-orthogonal states, distinguish them, or just learn all of them is hard. And sometimes you require many copies. Okay. No question, then okay, it's a bit tricky. We have 15 minutes. Okay, maybe let's try to start this for now, and then we'll repeat next time. Okay. Okay, so let's close up the quantum information and let's go back to measurement. And this is something I think we said we will do, and now we can do. So we say we kind of generalize everything from the computational basis projective measurement. Okay. And but we have a generalized measurement that doesn't look like projective measurement at all. We have those MIs. Okay. Maybe I'll just go here. Okay. So we have those MIs that doesn't look like projective measurement at all. But actually, we can kind of think of them as projective measurement also, just on a larger space. Okay. So I think this is quite interesting. Okay. So actually, you can get generalized measurement by just doing projective measurement, and I guess you do a unitary and a projective measurement on a larger space. So what we will do is this, and so we have our quantum system here. So this is Q, and you have some state side. And you want to do some generalized measurement with those operator m sub m. Okay, so it's a little confusing, but whatever, we are following the textbook notation, so we have big M sub small m. Okay, and we want that when you do the measurement, the state become like this m small m on side, right? With some probability. And how we do this is we will get an ancilla system. Okay, so it's whatever system, but it should have large enough size. Okay, so what's large enough size is whatever number of measurement outcome here should. So number of so the dimension here should be bigger than the number of outcome here. So for every outcome, there should be also normal basis element here. And yeah, so you have your general system. We want to do generalized measurement, and you can do that by using an ancilla system. Then you do some kind of unitary, and then you do just the computational basis element on here. Okay, and so really you are encoding your original measurement just in this weird unitary, and this weird unitary is actually in pretty good form. Yeah. Oh, we are talking really quick. Anyway, so we are thinking, okay, so I should do. Okay, so we have this ancilla system that's, so at least number of m dimensional, okay. And so the ancilla system starting on 0. Okay, so hopefully the m also counting from 0. And okay, and so this unitary should do this thing. So it should rotate your system and 0 into your the post measurement state you want is n sub m psi, and and rotate. So it rotate the q part into this, and rotate the big M part to small m, and sum over all small m. Okay. And so you see, if you got this thing and you measure this part on computational basis, and then you will get exactly this measurement outcome state. So because you project it into small m, then so do we write it in somewhere here? Okay, so yeah, so it's down here. So okay, 10 minutes. Okay, so let's skip the non-improved part. Okay, so we want this kind of a unitary to exist. Okay, and so let's be a little careful about all the information here. So here, so information about measurement m. So those things are, so u depends only on the information small n here. And here we have input state side. And the input state side should be independent of your measurement you do, right? So this should be whatever. And this psi is independent of m and is independent of your u. And so, for example, if you put another input, say phi, then it should satisfy a similar relationship here. Okay, so you are just turning phi here, psi to phi here, and psi to phi here, and you are using the same u, and you're getting the same m. Okay, and here we m to m prime, but that's just we want to change dummy variable. Doesn't matter because it's getting summed over. Okay. So whatever input you should get so whatever input side you should get a similar outcome, and this u depend on m. Okay. And okay, and I guess let's do a sanity check. So this u should be unitary, but they actually exist, and let's do a sanity check. That's we do the inner product of those things to see that this u actually preserve length. Okay. So, so we do inner product on both sides. Then on this side, you get those two inner product, and so that's this side 0. Sorry, this is phi to phi. So phi 0 and side 0. And so on the left hand side it becomes this, and on the right hand side is the inner product between those two things. Okay. And I forgot to change this. Yeah, anyway. Yeah, on the right hand side is the inner product between those two things. And okay. And so on the left hand side you can see those u dagger u should cancel each other, and the 0 inner product with 0 is just 0 inner product with 0 is just nothing, so this is just inner product with psi and phi. Okay, so the middle step is wrong. Okay. So this is equal to psi, but anyway, this is phi psi and 0, 0. So this is phi psi. And on the right hand side is this very complicated expression, there is m prime and m. But then we know the m prime and m, they are also normal bases. So this thing is really delta m prime and m, and then you can get this delta function to get rid of one of the summation. So you are really just summing over m. Okay? So it's just psi, m dagger, m dagger, and psi. Okay? And then we can do our usual linearity, so we can put a summation inside and see that the summation thing is identity because you have the completeness of your measurement. So this is psi phi, and as we say, it's so the right hand side equal to this inner product, and the left side is the same inner product. So at least since that if you satisfy this equation, you are still preserving your length. So that's good. And okay, but I guess we also finish the proof. And yeah, so that's how much I want to do here. And so probably not this week's homework, maybe next week's homework. Then you can show that actually this is enough for this u to exist because. So this part is good for inner product. Then you can kind of extend it whatever to full matrix, and that still stand unitary. But I think it's not too interesting. So maybe we'll get rid of this year question mark. I'll think about this next week. But yeah, but this is something you can think about. You can do. This is something you can do, okay? And so here we just claim that this u exists, okay? And sorry so that's a really long digression, but back to what we want to do. We want to do generalized measurement, and now we say we have a unitary do this thing, and then we say we do a computational basis measurement on just the register. And then should give me a generalized measurement on the first register. And why is that true? Then we can go here. Okay. And so what do we mean by a computational basis measurement on the second register? Then we can write that as a generalized measurement. Anyway, so we can then let's actually generalize measurement with this kind of measurement operator. So you have projectors, the computational basis projectors on the second register, and you just do identity on the first register. Makes a lot of sense, I think. And yeah, so you do this on Q and M, and then 3 minutes, okay. Yeah, then yeah, then let's go through the calculation. 3 minutes should be enough. Then you can see the probability. Okay, so we need to check 3 things. We want to check the probability is the same as the probability you do generalized measurement, and the post-measurement state is the same as the post-measurement state you get. Okay. So probability, and so this is a projector, so is M dagger is just PM. Yeah. So probability should be your state bra and the state cat sandwiching your M dagger, MI dagger, MI. But MI dagger, MI is just PI, and yeah, and the PM is this thing. Yeah. And anyway, so then you expand those things, and we know this thing is up here, so we use this equation. It's ugly, but let's just write it down. So this part we have, let's see. Okay, it's annoying. So we already have an m here, so we have different m for our dummy variable. So we have an m double prime and m prime. So this is u psi 0 part that we expand it into m double prime. Okay. So it is big M small m double prime psi tensor small m double prime. Okay. Okay. Just check here. This basically this equation just small m becomes small m double prime. Okay. And similarly, the previous part is the same thing. You just flip k to bar. And okay, so you have m prime. So the m double prime is m prime here, and this thing you get dagger, then it's psi k and m dagger m prime. And the middle part, as we say, so PM is this thing. Okay. So it's identity on Q tensor projector of M on here. Yeah. And then you see you have a lot of delta function. You see all those m prime, m, and m prime. But there are also no bases, so you sum over m prime and m double prime. The only non-zero thing you can get is when m prime equal to m and m double prime equal to m. Okay? And yeah, so let's skip the delta function part, and so you just put all the m prime and the m double prime to m, then you left with psi m dagger m sub m dagger and the identity and m sub m and the psi, and then there's a tensor part we didn't say, then tensor part is 1. Tensor part is like m, okay, equal to this is 1. Okay. Yeah, and this is the probability that you think you should get, and we're over time, but post measurement state. So we'll continue next time, and then we'll see the post measurement state give you this n sub n psi on the Q part. Okay. And yeah, and that's what you expected when you do generalized measurement. Okay, so I think that's time for today, and next time let's continue on this QM2. Okay, any question?